Okay, just a reminder, we'll have our exam this Friday. It covers all material that we discussed through last Friday. And today's example is not new material. Just think of it as a supplement to last Friday's material. Just want to do another example of sketching the Bode magnitude plot. And in particular, we're sketching by hand what we call the asymptotic lines. Those are the straight line approximations. All right? So if you just stepped in, please make sure you pick up one of these pieces of paper, and we should be able to get it done on one piece of paper this morning, okay? On half of one piece. All right, so again, I'm going to just review the steps that I take. And so the first thing what I'll do is I will determine all the basic factors. Okay. Let me kind of turn off the autofocus for a moment there. Let's zoom in. Okay. All right, so let's determine the basic factors. Okay. Okay. So one of them is determine the Bode gain. Okay. And remember, the Bode gain is you let S go to 0, ignoring 1 over S and S terms. Okay. You need to ignore terms that are 1 over S or S, because if you let S go to 0, 1 over 0 goes to infinity. And we can't plot that. Even if we take the log of it and do it in dB, that's still infinity. If you let S go to 0 here, then you get the gain is 0. And when you take it in dB, you get minus infinity. So neither one of those is easily plotted. It will shift the picture up and down. So what we do is we do the Bode gain. So the Bode gain in this case, we let S go to 0 everywhere, but ignoring this term here, then we get 240 times 5 divided by 0.3 and 900. Okay, so that's the Bode gain. And so somebody please convert that to dB. Okay, we're doing the Bode magnitude plot, so everything needs to be scaled in dB. 13 dB. $250, $240. Do we have a second? Is it 13 dB? Okay, let's sort this out. 240 times 5 is, oh, there's some cancellations there. But 13? Okay, we got several people who said 13. Let's make it 13 dB. All right, that's one thing. The next thing we do is I list all the other factors that I've got. Okay, so I got 13 dB is one, and then I've got this factor. Oh, I'm sorry, this is a 0, not a pole. This is a 0 at omega equal to 0. It's the numerator term. And so what that means is the initial slope is plus 20 dB per decade. Okay? A line that looks like this. Okay? That's the initial slope. I've got a pole at omega equal to 0.3. Okay? So what that means is that the change in slope is negative 20 dB per decade. Let's continue on. I have another 0 at omega equal to 5. So the change in slope is plus 20 dB per decade. And then finally, I've got a complex poles at omega n equal to square root of 900. Okay. And the change in slope, the slope change is going to be negative 40 dB per decade. Okay, so that's all the pieces of information that we need in order to sketch the Bode magnitude plot. Okay. All right. The next thing we do is label our axes. Okay, label the axes appropriately. The horizontal axis we would label frequency. The default is omega, so it's radians per unit time. You know, if you want to say unit seconds, you can do that if you wish. Radians per second, radians per hour. Kind of depends on some additional information somebody has to tell you whether or not the time measurement unit was seconds or days or something like that. Okay. If we're looking at the frequency response of this room's temperature characteristics, we'd probably be measuring on the order of minutes or hours. If we're looking at the frequency response of a electric motor, its position response, we would be looking at radians per second. Those things. Okay. Vertical axis, we're going to call it something like gain or magnitude, and the units are going to be this. Okay. Technically, it's not like a unit. It's just 20 times the log. Okay, so remember dB in this course is 20 times the log base 10 of whatever gain it is that we're dealing with. So this is our definition of dB in this class. Okay. So we've got our basic factors, and we label our axes. So let's go ahead and do that this morning. Fortunately for us, the exam on Friday will have a staple up in the upper left-hand corner, so the paper should not be upside down. But we do need to know how to use semi-log paper. Okay. Remember, high frequency is compressed, low frequency is expanded. So we should get this pattern like this. So we're going to label this frequency. Radians per second. And we need to get all our breadcrumbs, so we're going to put all our breadcrumbs on here. So we're going to label the axes appropriately. What I do is add breadcrumbs. On frequency axis. Okay. And so the breadcrumbs I need to add 0.3, 5, and 30. Okay, those are the numbers I need to do. Okay. So 0.5, 5, and 30 needs to fit on here. And so I think I'm going to maybe put, let's see, if I put 1 here, 10 here, 1 here, maybe I'll put 1 here. 1, 10, 100, 0.1. Okay. Find your major divisions, label them. Okay. This is 1,000. Let's put in our breadcrumbs. We have one at 0.3, so here's 0.1, 0.2, 0.3. And then I have one at 5. 1, 2, 3, 4, 5. And then one at 30. 10, 20, 30. Okay, so those are my breadcrumbs on the frequency axis. Okay. The Bodie gain is 13 dB, so I need to make sure 13 dB is going to be on the scale. And so maybe this morning I'll do this. I'll say, let's put 0 here, 10 here, 20, 30, 40, minus 10, minus 20, minus 30, so forth. This is magnitude in dB. So we're ready to start. Okay. Okay, so this was the transfer function. We listed the basic factors. And not only did I list the basic factors, but I also wrote down what was the change in slope. Okay. We've got our axes labeled. We've got our breadcrumbs on the axes. Now what we're going to do is we're going to start on the left side. This is low frequency. Okay, start on the left side at low frequency. And what we want to do there is we want to sketch the correct slope. We want to get the initial slope correct and account for the Bodie gain. Okay. So in this particular case, what we have here is the initial slope is going to be plus 20 dB per decade. And the reason is because of this S in the numerator. Okay, due to S in the numerator, we have to start off there. Okay. So we need to put in a line with this slope on our paper. Now we also need to put that line vertically up and down on our paper in the right place. And what I typically do is I go find omega equal to 1. And then this dot here, over here, this needs to be the Bodie gain. Okay? So on the vertical axis, you need to put this dot on the vertical gain. Horizontally, side to side, you need to put it at omega equal to 1. So omega equal to 1 and the Bodie gain and the slope. That will take care of several terms in our list of basic factors. We're trying to take care of this Bodie gain and this 0. Okay, low frequency, omega equal to 0. Okay. So I come here and I say, here's omega equal to 1. 13 dB is right about here. And we want to have an initial slope of 20 dB per decade. So we need to have a slope that looks something like maybe something like this, okay? But it needs to go through that dot. So 1 decade away at 10, we would be up 20 dB, so 20 plus 13 is 33, so we would be something like about here. Okay? 1 decade this way, I would be 20 dB below that, so I'd be at minus 7. That's somewhere about here. Okay, so I need to connect the lines like this. I start at the low frequency, I get my initial slope correct. So I need to draw a line that looks something like so this is the idea. Start off at the low frequency side. At low frequency, these terms haven't come into play yet. The only term that's come into play is the Bode gain. It's just the picture up and down, and the initial slope, omega equal to 0. So if I've done everything right, this slope is 20 dB per decade. 20 dB per decade. And I've taken care of here the Bode gain. All right. There's the instruction. Start on the left side, sketch the correct slope, and account for the Bode gain. All right. Next instruction is to extend the line toward the right hand side. In other words, we are increasing frequency. We're increasing the frequency omega. Okay? But what we do is we adjust, we change slope at each corner frequency. At each breadcrumb. Okay? And just again to review, my breadcrumbs are 0.3, 5, and 30. 30. 0.3 was a pole, negative 20 dB per decade. 5 is a 0, plus 20 dB per decade. 30 was a complex, so it's minus 40 dB per decade. These are changes. Okay. We already had this written down, but I'm just writing it down again here, just to emphasize what we're trying to do. So I need to draw this line. I need to extend it until I hit a corner. Here's a corner, so I do this until I hit 0.3. Now I got to change it right here, make a change. And it's minus 20 dB per decade change. So now the new slope is 0 dB per decade. Okay. And I go out to 5. 1, 2, 3, 4, 5. Here I got to make another change. Here's a breadcrumb. And at 5, I see the change is plus 20 dB per decade. So this thing starts rising again. dB above this is about like this. Okay. When you draw that line, like so. So we extend that line till we hit the next corner, which is right here. I look at my list of breadcrumbs. Let's see, I've taken care of this one. I've taken care of this one. I got to do this one, minus 40 dB per decade. And so the result is going to be negative 20 dB per decade. Like so. Okay, so these are the asymptotic curves. The general shape is correct from a straight line perspective. The actual response, if I were to sketch it in, is probably going to look something like this. A little bit of error here. A little bit of error here, like this. This second order term, we could take a look at the second order term. You know, this number has not been accounted for in the straight line approximations. But if we were to account for it by using, say, the computer to calculate, we'd find the damping is a little bit low. So we probably would not be surprised to see if there may be a little bit of peakiness here. And so it might do something like this. Okay. So the actual frequency response may look something like this. So we would conclude our comment by just saying, realize that the actual curve deviates around corners. Okay, near the corners there would be some deviation. Any questions? What should we do with this space? Anybody got a suggestion? No suggestions? Concerns? If you'd like to stick around and use that space, I'll come up with another example to do, but otherwise, you're free to go. I'll stick around and do another example for those who want it. Okay, so I see a few people have stuck around, so what I'll do is I'll do another example for those who would like to see it. We'll use this lower space right here. Let's do that one. Okay. Let's step through the processes again. Let's write down our basic factors. Bodie gain, The Bodie gain in this case, we let S go to 0, ignoring terms like this. And so the Bodie gain is 20. 20 you have to convert to dB. I think that's 16. Is it 16 dB? 13 dB? I think it's 16 dB. 26? 26 dB. Okay, 26 dB. I'm sorry, 26 dB. That's right. Because 10 would be 20 dB. So double that, that's 6 dB more. Yeah, 26 dB. I'm sorry, 26 dB. 26 dB. Okay, and then the other terms, the other factors we have is we have two poles at omega equal to 0. So that tells us that the initial slope is, because these are poles, it will be negative 40 dB per decade. Very good. Okay. And then we have a 0 at omega equal to 20. And so that tells us that the change of slope is plus 20. Okay. And let's label our axes. Frequency axis, radians per second. I don't need to worry about, I need to make sure 20 is somewhere on here. So maybe I'll put 1 right here, 10 right here, and 100 right there. This axis over here is going to, let's call it gain in dB. I need to make sure that I've got the vertical axis in such a way that 26 dB is somewhere on the page. Oh, I think I'm going to put 0 here. And I'll say 20, 40, minus 20, minus 40. Okay. Notice that I tend to do something that's divisible by 20. So because our slopes tend to be multiples of 20 dB per decade. So again, you kind of want to pick a scale where it's easy for you to figure out the slope that's a multiple of 20 dB per decade. Okay. So what we need to do is we need to take care of these two terms first, the Bodie gain and the initial slope. So just take care of the Bodie gain, the initial slope. So the initial slope is minus 40 dB per decade, and it's got a Bodie gain of 26 dB. And so when I take care of these two factors, I would draw a line like this. The slope should be minus 40 dB per decade. I look for, on the horizontal axis, I look for omega equal to 1, and it needs to come in vertically at 26 dB. So this pair, omega equal to 1, 26 dB, I need to find that dot on my paper. So here's omega equal to 1, 26 dB is, let's see, here's 20, 40, 30, 26 is roughly there. Okay. I need to draw a line that goes through with a slope of 40 dB per decade. Okay, so 40 dB per decade is going to look something like this kind of slope. Okay. 40 dB, but I need to put it right through here. So let's spend a minute thinking about how that might look. 1 decade away, I'm going to be over here, 1 decade away. I'm going to be down 40 dB. This is 26. 26 minus 40 is negative 14. Negative 14 is somewhere about here-ish. And the 1 decade this way, I need to be 40 dB above 26, so that's 66. It's somewhere about like here. So I need to be drawing a line that looks something like this. Okay. I have only one other factor that needs to be dealt with, and that's omega equal to 20. So omega equal to 20 is right here. Okay. And so I basically stay on this line until I hit this point, and then I need to change the slope. So I need to change the slope right about here. The slope change is plus 20 dB per decade. So it's still going to go down, but it's going to go down at a less aggressive slope. So it's going to be something like this. So this slope is minus 40 dB per decade, and this slope is minus 20 dB per decade. And here's the Bode gain at omega equal to 1. Okay. And the actual curve will be pretty much along these lines, except near the corner, it's going to here probably do something like this. There's going to be about roughly a 3 dB error. Okay. So this is G of S plus 20 over S squared. There. All right. Now, on Wednesday, we're going to look at the phase. Now, if you can do magnitude, then I'm going to tell you you can do phase. We're going to follow the same type of idea. We're going to draw little breadcrumbs. We're going to be changing the slopes. The only difference is we have twice as many corners to deal with. Okay, phase plots just have twice as many corners. But if you can do magnitude, then you can do phase. Yeah, all right. Any comments? Okay, that's it. Y'all have a good week. See you Wednesday.
I usually won't be on Fridays too.
Yeah.
But maybe we will.
Yes.